Hi everybody. In this video, we're going to finish the second half of our introduction to logarithmic functions. So we're finishing this topic. Yeah, 18.2.1, Introduction to Logarithmic Functions. We finished off with that purple example last time. And now we're going to dive right into graphing log functions. It's going to be pretty similar to graphing exponential functions. And there's going to be some similarities there, but also a couple differences too. All right, so first step, this is so important, and this is a step that commonly gets missed. Please don't miss it. So important. When you're graphing log functions, first, don't forget it. Highlight it. Star it. Do what you need to draw attention to it. Don't forget it. First, you're going to convert the log equation into exponential form. If you don't do this step, your graph's going to be totally messed up looking. So first, remember again, star it, highlight it, draw attention to it, don't forget it. Convert the log equation into exponential form. Okay, the y variable will be your input this time. So because of that, because you're switching it around into exponential form, your input is going to be your y variable. So we're going to choose our values for y, and we're going to substitute them into the equation to get our values for x. Then we're going to plot the points. Characteristics to keep in mind. So characteristics to keep in mind, the graph can only appear to the right of the y-axis because the domain is going to be restricted to positive values of x. The graph gets close to the y-axis for small values of x, but it's never going to touch it or cross it. The point 1, 0, here again is that word I don't really love. It will almost always be a point plotted on your graph. So just like in exponential form, we had the point 0, 1 that's almost always on our graphs. Well, this time it's going to be 1, 0 that's almost always plotted on our graph. So here we go. This is one of those ones that's going to be messy. We're going to put 3 different graphs on all the same grid. We also have to sneak in 3 tables into this space that we have down below, because we're going to put all 3 of these graphs and all 3 of their tables on this grid and in this space. So just make sure you're writing small and you're leaving yourself some space and some room. Okay, so what was the first step that I said? Highlight, don't forget it. Make sure you do this step. We're going to take this function of f of x and we're going to first, what is it? Convert it. Convert it to exponential form. So I'm going to take this and it's going to be f of x equals log base 2 of x. And we're going to convert that into exponential form. So if you want to, you can write log base 2 of x equals y. And then we're going to convert it. 2 to the y equals x. So this one is going to be 2 to the y equals x for this function. So now we are going to draw up our table. And so we're going to have x, and we're going to have 2 to the y. And we're going to have our y, and we're going to have our ordered pair. Now this is going to look a little bit different because what's your input this time? And your input is the variable that's on in our equation. And so remember too, from up here, step number 2, the y variable is going to be our input. And so 100% of the time, we are going to use the values just like we did for exponential of -2, -1, 0, 1, and 2. So you can fill those in, and we're filling them in for the y's, again, because we converted our log function into exponential form. Let me get this. Because we convert it into exponential form, our y's are going to be our inputs. All right, here we go. So this time we've got 2 to the -2, which is going to be 1 over 2 squared, which is 1/4. So we're going to be graphing the point 1/4, -2. And then we're going to have 2 to the -1, which is 1/2. And that 1/2 comes over here. And then we're going to graph the point 1/2, -1. Then we're going to take 2 to the 0, which equals 1. And so we're going to plot the point 1, 0. Then we have 2 to the 1st. And then we're going to plot the point 2, 1. Then we have 2 squared. That's going to give us 4. Then we're going to have 4, 2. All right, so let's go graph those. Keep in mind our next 2 points. So I know, again, we have this where it's going to be 1/4, -2, but we're going to have 2 other points that we're going to have to squeeze in there. So just do the best that you can here. So 1/4, -2 is going to be about right here. And then we're going to have 1/2, -1. Then we're going to have 1, 0. Then we're going to have 2, 1. Then we're going to have 4, 2. If you wanted to, you could do the next one where let's say if we did 3, and it'd be 2 to the 3rd, and that's going to give us 8. So you could graph the point 8, 3. Let's see here, 5, 6, 7, 8. So it's 8 up to 3, and we could graph that one. All right, so we've got this line. There's your log curve. All right, so now let's look at our next function that we're graphing. So the next function that we are graphing is this log base 3 of x. So I'm going to choose a different color for this one. I'm going to do blue. Again, log base 3 of x. What's our first step? Convert it into exponential form. So it's going to be 3 to the y equals x. So 3 to the y equals x. If you wanted to, the next one is, I think, our base 4, right? We could just go ahead and do our conversions right now. And it's going to be log base 4 of x equals y. So it's going to be 4 to the y equals x. And that's going to be our third equation that we're going to deal with. All right, going back to blue. So we've got our x, and we've got our equation of 3 to the y, and we've got our y, and we've got our ordered pair. And again, we're going to do -2, -1, 0, 1, and 2. And now we're going to plug that in. So we've got 3 to the -2 to the -2 power, which is going to be 1 over 3 squared, which is 1/9. So it's going to be 1/9, -2. Then we're going to have 3 to the -1, which is 1/3. And so we're going to have 1/3, -1. And then we're going to have 3 to the 0, which is going to give us 1. Then we're going to have 3 to the 1st, which is 3. So we're going to graph the point 3, 1. And then we're going to have 3 squared, which is 9. And we're going to have 9, 2. All right, so now we're going to graph that one. And again, so our 1/9 is even closer to the y-axis. And then we've got 1/3. And then we've got 1, 0 again. Again, my graph moved on me from last time. Because again, that would be kind of more down here. But again, my graph shifted up on me a little bit. And then 1, 0, and then we've got 3, 1, 1, 2, 3, 1. And then we've got 9, 2. So 6, 7, 8, 9, 2. And we're drawing our graph. So you should predict, what do you think is going to happen with our purple graph with this 4 to the y equals x? So looking at the trend line, I'm hoping you're going to say, well, it's probably still going to cross at 1, 0, which is going to be correct. For these values in this range of our x's, it should get closer to the y-axis. Once we hit 1, 0, for once we get over here for the x values, it should get closer to the x-axis. So let's draw up our grid. For the next one, let me erase some of this and I'll create some space right here. All right, next one, we're going to have x, and we have 4 to the y, y, ordered pair. So -2, -1, 0, 1, and 2. On your mark, get set, go. 4 to the negative 2, which is going to give us 1/16. Negative 2, then we've got 4 to the negative 1, which is going to be 1/4. We're going to graph the point 1/4 negative 1. We're going to have 4 to the 0, which is 1. Then we're going to have 4 to the first, which is 4. We're going to graph the point 4, 1. Then we've got 4 squared, which is going to give us 16. And then we're going to attempt to graph the point 16, 2. Okay. My points. So the first one's going to be 1/16 negative 2. So it gets even closer. And then we've got 1/4 negative 1. Again, that even gets closer. They intersect at 1, 0. Then we've got, what was the next one? 4, 1. And then, so by the way, my blue line should have gone up a little bit higher right there because my lines won't intersect. And then we've got 16, 2. So 16 is going to be way over here. We're just going to call it 16, 2 about right there. And so draw your line. Again, just do the best you can. And we're going to make some observations just like we did last time. So observations to note for our base being greater than 1. All 3 graphs intersect at 1, 0. Graphs cross x-axis, but not the y. Oops. Not the y-axis. And as base increases, so as b increases for x values greater than 1, what does the curve do? Curve gets closer to what? X-axis. And then I'm not sure that my next bullet's going to fit there, so I'm going to move it over to the left a little bit. So you guys can put yours right here. I'm just out of space. The next one, as base increases and for x values, oh, that's supposed to be the word values, but I spelled it values. I'm going to sneak a little u in there. For x values greater than 0, but less than 1, the curve does what? Gets closer to the y-axis. All right, so I abbreviated some of the words in there, but that says as base increases and for x values greater than 0, but less than 1. So again, that's going to be for situations like that. Greater than 0, less than 1. The curve is going to get closer to the y-axis. All right, so now we're going to graph them for when our base is not greater than 1, but for when it's in between 0 and 1. We're going to try those two. So what's our first step again? Always, always, always for log functions, we're going to convert. So we've got log base 1/2 of x equals y, and log base 1/3 of x equals y. And so it's going to be 1/2 to the y equals x, and 1/3 to the y equals x. So there are our two functions that we've converted into exponential form. I'm going to go ahead and make the first one purple. So we're going to have x and then our function of 1/2 to the y. Then I'm going to have y, and then I'm going to have an ordered pair. So then we're going to have, again, -2, -1, 0, 1, and 2. And then we're plugging that information in. So 1/2 raised to the -2nd power. Recall again, oh, my neck is stiff. All right, recall again that if we have 1/2 and it's raised to the -2nd power, we can switch it. So it's like this to have the positive exponent. So that's going to give us 2 squared, which is going to give us 4. So then we've got 4 -2. And then here we're going to have 1/2 raised to the -1st. Again, it's going to be 2 to the 1st, which is going to give us 2. So then we're going to have 2 -1. Then we're going to have 1/2 raised to the 0 is going to give us 1. Then we're going to have 1/2 to the 1st power, which is going to give us 1/2. And then we have 1/2 raised to the 2nd power, which is going to give us 1/4. Because again, that's like 1/2 times 1/2. Which is going to give us 1/4, 2. So now let's go graph those. So I've got 4, -2. So 1, 2, 3, 4, -2. And then 2, -1. And then 1, 0. And then 1/2, 1. And 1/4, 2. All right, I think that's good for that. So let me draw my grid. It's going to look something like that. What else? Let's try our next one. I'm going to put this one in blue. So we've got x. We've got this time 1/3 raised to the y. And we've got our y, and we've got our ordered pair. And so it's going to be -2, -1, 0, 1, and 2. Yeah, I probably didn't need to make my lines that long, did I? Don't know what's going on there. I just like erasing today. Therapeutic, right? Let's get rid of our mistakes. Okay. 1/3 raised to the -2nd. So again, that's going to be like 3 squared, which is 9. And that's going to be 9 -2. Then we're going to have 1/3 to the -1st, which is going to be 3 to the 1st, which is 3. So then we're going to have 3 -1. Then we're going to have 1/3 to the 0, which is going to be 1. Then we're going to have 1/3 to the 1st, which is going to be 1/3. So it'll be 1/3, 1. And then we're going to have 1/3 squared, which is going to give us 1/9. And it's going to be 1/9, 2 for that. All right, so let's go graph those. So we've got 9, -2, which is going to be right here. Then we've got 3, -1. So 1, 2, 3, -1. Then we've got 1, 0. Then we've got 1/3, 1. And then we've got 1/9, 2. All right. All right, so what are our general observations? So the last one we talked about was for a base that's going to be greater than 1. Again, remembering that your base is right here. For this one, it's going to be for base values that are greater than 0 but less than 1. And we're still going to have that both graphs intersect at 1, 0. Graphs cross x-axis, but not the y. And then we've got as base decreases this time, And for x, so decreasing again, that means like we're going from 1/2 to 1/3. So that's a decreasing base. And for x values greater than 0, but less than 1. So we're talking about this portion of the graph, right? So what's happening in that trend right up above? The curve gets steeper and closer to y-axis. As base decreases and x values, and for x values that are greater than 1, the curve gets closer to the x-axis. Okay, so again, just being able to recognize just generically like what's happening with the curves. How does a log curve look different here for when our base is going to be less than 1 but greater than 0? Excuse me. Versus what it looks like here for a generic log curve where our base is going to be greater than 1. And then again, contrasting that with what does an exponential curve look like? So our exponential curve versus our log curve. So just be thinking about how those look different. So for example, like our log curve, not our log, our exponential curve would have looked like this, right? So because we would have the point of 0, 1, which is why those two are opposite operations of one another, exponentiation and logarithms, because look at that. Look at how the curves are similar. And they actually reflect across this y equals x line. That's also how they can relate to one another, that they are symmetrical across that line. Another cool fact. All right, so let's apply some log functions. We're gonna look at some word problems here. So we've got this function, it's defined by f of x, and it equals 27. Plus what you see, oh my goodness, plus what you see there in the equation, and it approximates the barometric pressure in inches. Okay, so our label is gonna be in inches because it says that our equation here, it's going to approximate the barometric pressure, but in inches, of mercury at a distance of X miles from the eye of a typical hurricane. Approximate the pressure 9 miles from the eye of the hurricane. So what are we plugging 9 in for? Are we plugging it in for X? Are we plugging it in for f of X instead, and we're solving for X? Like, which one is it going in for? And you should get it right here. It says X miles, and this is miles. So this is going to be plugged in for X. So now we've got f of 9 equals 27 plus 1.105 times log, and I'm not even gonna write the 10 down there. You don't need that 10 on there. And we haven't talked about that yet, but that's called the common log. And when it's log base 10, you don't have to put the 10 on there. So I'm not going to. And oops, instead of putting an X, I don't want an X there. I actually want to put 9 in there. All right, so then we get that. So then we have 27 plus 1.105 times log of 10. Well, you could use any one of you could use the change of base rule if you wanted to, or you could just, because your calculator has the button in there of a log base 10, you could just do log of 10. You could also use the rule. We talked about this rule in last time when I said, if we have a log where the base and the argument are the same, what did that equal? So log base 10 of 10, what did that equal? Because that's asking the question of 10 to the what power equals 10. So 10 to the what power gives me 10. And you should say 1. So that means that 27 plus 1.105 times 1, and you can put it in your calculator too if you want to, is going to equal 27 plus 1.105, which is going to give us 28.105. What's our label? Inches. So it's going to be 28.105 inches. Let's check out the next page. I hate this example. You know why? It has to deal with mice, and I hate mice. Some people hate spiders. You can give me the spiders. I will smash all the spiders for you. You hate spiders? Give me a call. I'll come smash the spider for you. If I have a mouse in my house, in my garage, outside running across my shoe, I'm gonna jump up and scream, and I'm not gonna be happy about it. I hate them. They're disgusting. Anyway, so we're gonna look at this example. It says a study showed that the number of mice, in an old abandoned house was approximated by the function defined by fill in the blank, where t is measured in months and t of 0 corresponds with January 2008. So here our first one says to find the number of mice in the house in January 2008. Well, what that means is we're plugging in t equals 0 for this one. So we're going to find m of 0, and that's going to be equal to 6 times log base 4 of 2 times 0. Oops, I need to put another, there we go. Oh, I'm sorry, no I didn't. You don't need the extra one. All right, sorry about that, guys. All right, 6 times log base 4 of 2 times 0 plus 4. And we're going to have 6 times log base 4. 0 times 2 is 0, so it's going to be log base 4 of 4. Guess what we get again? Log base 4 of 4, what does that equal? We should know this one by now. 1. 6 times 1. If you don't remember, go back, look at the previous example. Go back, look at a previous video. We talked about that rule. All right, 6 times 1 equals 6. And ew, what are we talking about? Ugh, mice. Okay. Next one, because we love mice, let's just keep talking about them. Make me gag, make my skin crawl. All right, July 2008. I'm just going to tell you, save you this trouble of going back. It's going to be t equals 6. And this next one is going to be t equals 30. Just trust me on this. T equals 6. So we're going to have m of 6 equals 6 times log base 4 of 2 times 6 plus 4. 6 times log base 4. 6 times 2 is 12. 12 plus 4 is, what is it? 16. So 4 to the what power is going to give us 16? 4 to the what power? 4 to the what power is going to give us 16? That's the question this is asking. 2. 6 times 2. And that's going to equal 12. 12 mice. Gag. Okay. I don't believe this next one, by the way. Like, we've only gone from 6 to 12 mice in 6 months. I don't think so. All right. Whoever came up with this equation, I'm not sure about their research and their data collection. It's not true at my house. Well, not my house, but my husband's shop, and ew. Okay. M of 30 equals 6 times log base 4 of 2 times 30 plus 4. And that's going to equal 6 times log base 4. 30 times 2 is going to give us 60, and then 64. So 4 to the what power is going to equal 64. And you may not remember this one, I don't know, but you can also, don't forget, you can also go like this. Our change of base rule that we talked about in the previous video could be log of 64 divided by log of 4. If you're not sure what that is, you don't have to guess and check, but you might already know it too. It's 3. So 6 times 3, and that's going to be 18 disgusting, nasty little mice. Nasty. Okay. That is the end of this video, right? Not too long. And then in the next video, we're going to talk about properties of log functions. So thanks for tuning in.